this talk is about the relationship between logic and computation and programming with types in particular. I introduced this topic in my undergraduate course on functional programming with Scala in the university, mainly for theoretical reasons, to show this connection between these two scientific fields. But we also introduced this topic in Habla computing in our training courses in Habla, because I think this topic on logic and computation is give us great samples for practicing with algebraic data types and type-driven development. The motivation for this talk is that, in my opinion, the interplay with logic and computation makes for very good, compelling arguments in favor of strongly typed languages like Scala. When we talk about the advantages of programming with types, we usually refer to the improvements in documentation, better IDEs, early error detection, and so forth. But to type or not to type is also a matter of logic. And when we say that it's a matter of logic, we are not referring to common sense. We are talking about formal logic, deductive arguments, and logical reasoning. As for instance, when we say that the Scala programmers are passionate functional programmers and passionate functional programmers are crazy about logic, therefore we can conclude that Scala programmers are crazy about logic. This argument is an instance of a more general pattern of deductive reasoning known as the Barbara Syllogism, studied by Aristotle some time ago, which says that all A are B, if all A are B and all B are C, therefore all A are C. The important point in this argument, this kind of argument, is not whether you agree or not with A, with the truth of the premises, but the point is that you have proven these premises, these implications, these premises, then you are forced logically to accept the conclusion because you can build a proof for it. So, the purpose of this talk is answering these questions. How is logic, how is this kind of arguments, deductive arguments and logic related to programming and programming with types in particular? Do we program more logically when we are programming in Java, in Scala or Haskell than when we program in JavaScript or Python? And in general, does logic help us to be better programmers? So in order to answer these questions, we will use a little example on function composition in order to introduce type-driven development, which is the key to state in a very precise way this relationship between logic and type and computation. Okay, then if we have time, we will spend some more time with more examples on this interplay between logic and type-driven development and logic, and finally we conclude with some proofs. Okay, so let's start with this little example on function composition. Let's say that we have this length function, okay, for strings. Can also implement an event function, which is an integer return a boolean in case that this boolean even. Okay, we would like to implement a function with even length, which receives a string and returns a boolean. Boolean value, we return true if the length of the string that we receive, okay, is even, false otherwise. Okay, This function, this is even length function, can be implemented in a more modular way if we focus on the composition aspect. What we would like is to get a more reusable component composed, okay, which which allow us to make the composition not only of the is even, okay, and length function, okay, but in general, two arbitrary functions, okay. So what we have here is that what we want is not is even the length function, okay, but what we want is to implement a function, okay, that receives a function f, okay, which gives us some integer and compose it with a function from into Boolean. Okay, so we have here more, of course, what we have here is the active return function, okay, and this implementation allow us to implement our is even length function in a more modular way, reusing this composed function, okay. So what we want here is compose is even with the length function like this to x, and here we have some modular definition. This definition is made of a general reusable component composed and two particular functions. Okay. Of course, we can make this composed function more generic because actually the implementation of this function does not depend on the actual types, input and output types of these functions. Okay, so instead of a string, we can have an A. And similarly, we can abstract away the particular integer type and use B type. And similarly, can replace Boolean with any type C. And what we get here is a fully generic function composed, which allow us not only to compose functions from the previous signature, but functions with any input and output type, provided that the output type of the function matches the input type of the G function. Okay, so the way in which we implemented this function was rather empirical. We were told that I want to implement a generic function that receives the functions and compose, and we abstract away from the particular details of a very specific even length function. Okay, but in order to illustrate type-driven development, what we are going to do is to play a little game. Let's say that we hide the name of this function, and instead of compose, we give us some hints about the intention of this function. Let's say that we call it foo, and we handle this function to some colleague, which is an expert in functional programming and type-driven development, and tell her to implement this function. Can it be implemented just by using by looking at the signature of the function? Well, the answer is yes. How do we implement this a function with this signature? What we do is reasoning in the following way. Okay, we have to implement this function, which means returning a value of type AC. A function which receives A and returns a C. Function types are algebraic data types, and algebraic data types can always with two kinds of operations: constructors and destructors. Okay, destructor of service, deconstructor, whatever you name it. Constructors allow us to create values of this function type, okay? And destructors allow us to extract information about values of this type. In the case of functions, the constructor is lambda expressions. Lambda expressions are the way in which we create a function type, a function value. And the structure is function application, okay? So what our colleague is going to do is to look closely at the types of the values that we had to provide, the expressions that we had to provide, and to the types of the arguments of variables that we have available in order to implement our function. Okay, so we have to create a function of type A to C. We had to, without thinking too much, the only choice is to create a lambda expression. So what we do is to create a lambda expression of this type. Okay. Now our problem consists of finding an expression of type C, and now we are in a we are in trouble because C is C can be any type. It could be an int, it could be a boolean, it could be a type, and we do not have any constructor for this type. So the only way that we can obtain the way in which we can obtain a value or an expression of type C is by looking at all the variables and the information that we have in our environment. In this case, we have a variable, two variables f and g, which are this functions type, and we also have a variable, this value of type A. So how do we obtain a C? What we had to do is to apply this structure. We had to apply function application in order to see whether we can obtain the value. And we can, because what we have here is a function f that returns value of type C. So what we can do here is to apply this function, for which we had to find a value of type B. Now our problem is finding this value. In each step, the function compiles, okay? How do we obtain a B? Again, we can apply function application and obtain a B. But in order to do that, what we need now is a value of type A. And a value type A, we are lucky, we have here the value. So we got the implementation of this function, of this full function, of the composed higher order function, without actually being told by anyone what this function had to do. This is an example of type-driven development. In type-driven development, what we do is to program through a series of refinements, okay? In each step, what we have to do is to fill a gap in our code. And in order to fill that gap, we had to look very closely to the type of that gap and also to the type of the information that we have available in each at that time, okay? If we have to create a function type, no problem, we have constructor, it's a lambda expression. If we have to create a value of a generic parameter, we had to somehow observe the information that we have available, okay? So what has to do this with logic? Okay, let's come back to our Barbara syllogism. What we have here is that in order to give a proof of this syllogism, we can use different formal systems in logic. We can use Hilbert-style deduction system. We can use sequence calculus. We can use natural deduction. What we are going to do in order to give a proof of this syllogism is to informally use natural deduction. So a proof for this syllogism goes like this. I had two premises, B implies C and A implies B, and I had to prove that I had to give a proof that A implies C, okay, using these premises. Okay, how do we do that? What we do is to use a conditional proof rule, which is the introduction rules for implications in logic, in natural deduction proofs, okay? This rule says that in order to give a proof of this implication, what we had to do is to prove C, taking into account A as an assumption, okay? And how do we do that? Okay, if we have A, we have a proof of A, assuming that we have a proof of A and we have a proof of A implies B, then by modus ponens, which is the elimination rule for this kind of logical operator, we can conclude B. And again, if I have B and I have B implies C, by modus ponens again, I can obtain C. And so I can prove A implies C. So this kind of reasoning, logical reasoning, is in very close correspondence with the implementation and that we gave, and with the kind of reasoning that we applied when we were doing type-driven development. In fact, the signature of this compose function could be called perfectly Barbara, okay? Because if we look at function types as implications, okay, what we have here is exactly the Barbara syllogism, okay? This would mean that B implies C. If we have also that A implies B, then we can conclude that A implies C. So if we read the signature in these logical terms, reading function types as implications, what we have is exactly the Barbara deduction scheme. And what about the implementation? Well, the implementation is exactly the proof that we have given in this natural deduction style. And we can rearrange these signatures and program in order to see that this program is in a very close correspondence. This would be premise 1, okay? This would be premise 2, okay? This would be the implication. This is our assumption, okay? A. This would be A. This would be A implies B. This will be B implies C. Okay. What we have here now the relationship seems to be broken, but it is not, because what we can do here is to declare a variable of type C, which B, sorry, which is obtained by this application, and this will be this B, and then this way we obtain C. And finally, we have the conclusion A implies C. So what we see here is that we were doing type-driven development. We were implementing functional programming signature, and we were manipulating algebraic data types and constructing function types and observing function types. Well, it so happens that what we were doing was logic. In order to do that, the only thing that was necessary was to interpret functions as implications. And also, this is important concerning the implementation, is that when we have a value of some type in functional programming, in logical terms, this means that we have a proof. We assume in this case that we have a proof of the proposition corresponding to this type. Okay? So this is the correspondence known as the Carry-Howard correspondence, between which relates propositions with types and proofs with expressions, terms, or programs. Okay? And this is not casuality. We can find this correspondence in many other signatures that we can find, that we have in the functional ecosystem of Scala. For instance, in the library cats, okay, what we have is this bimap function, okay, and this bimap function we can apply it to the either data type, which is another algebraic data type with constructors left and right and destructors pattern matching. This is the way in which we extract information from a sum type, okay, with algebraic data types. And well, this bimap function has this signature for the either type constructor, okay, and we can play the same game as before. We can apply type-driven development in order to implement this function. What we can do, what we have to do here is to obtain either C or D. Okay? In order to obtain either C or D, again, we have to apply a constructor. We have either left or right. We can try to create a value of this type using a C. Okay. Then how do we obtain a C? We are stuck now. No, we are not stuck because we can advance in our implementation because we can obtain a C from this function f. The only thing that I need is an A. And now I am stuck. Now I am stuck because how do we obtain an A? Well, we have here either A or B. An A or B. We have to apply pattern matching and observe here whether we have an A or we have a B. Okay. In either case, what we have to conclude is with this value of type A. Okay. In either case, we have to conclude with C or D. This compiles, should compile. Okay. It doesn't compile because here it's a question mark. And now we can proceed with implementation. This branch is complete, but this branch is not complete. Okay, we have to choose between left and right. Left didn't work, so we have to try with D, and D will work because we have here G function, which needs a B, and we have a B. Okay. So again, this kind of type-driven development is a logical way of reasoning and implementing functions. Okay. Because and this is indeed something which is in the logic textbooks. This signature that we have here for either, if we interpret either with disjunction, what we have here is what it is called a constructive dilemma. Okay, which says that we have A or B, and A implies C and B implies D. Then we have, therefore, we can conclude C or D. And we have a natural deduction proof, right, which in principle has nothing to do with functional programming, but that corresponds literally with implementation that we did. Okay. Well, there are more examples. We have this product function in the semi-global type class in the cats library as well. If we instantiate this semi-global type class for function types which receive an A, what we have is this signature, okay? And this signature is what it is known as a conditional product. If we read, in this case, tuples and product types with conjunction, okay, with the AND logical operator, what we have is the conditional product. And we can transform, okay, these type-driven development implementations into a perfectly valid proof for this deduction scheme. Okay. So what we have seen is that there is a close correspondence between functional programming, programming with algebraic data types, and logic. And this can be summarized in this table. These are the constructors, of algebraic data types, exponents, products, and sums. Okay, and in logical terms, what we have here is that function types are implications. Okay, and the constructors and destructors of these function types corresponds to the conditional proof and modus ponens rules of the natural deduction formalism. Okay, products are conjunctions, and sums type corresponds to disjunction. Okay, and we can perform this double reading in these signatures, in many signatures of the libraries that we find in the functional ecosystem of Scala. So in conclusion, how is logic related to programming and programming with types? Well, they are two sides of the same coin. When we are writing this implementation of these signatures, what we are actually giving is a proof of a deduction scheme. In this case, the Barbara deduction scheme. Okay. This was discovered, and this is known as the Curry-Howard correspondence, and it was discovered by Haskell Curry and William Howard. And what they proved was that the work of Gensen, when he invented the natural deduction formalism, and the work of Alonso Charge, when he invented the type lambda calculus, was actually the same. In essence, they were inventing the same formalism. Okay, and this is something that it is not related only to this type of lambda calculus and the natural deduction style. It's something that pervades the logic and computing landscape. When we have different kind of logic, what we have is a computational counterpart. And so second order intuitionistic propositional logic corresponds to generic programming. Okay, and first order intuitionistic logic corresponds to dependently typed programming. We have classical logic. Classical logic has also computational counterparts. It is very related to control operators and the continuation passing style. Linear logic, which is another kind of logic, is very related to quantum computing and protocols and so forth. Modal logic to monads and verification, so forth and so forth. In sum, Aristotle, the first functional programmer. Okay, so does this mean that we program more logically that with strongly typed languages than with JavaScript or Python and so forth? Well, it is not that we program more logically. We can program logically, perfectly, in a perfectly logical way with Python and JavaScript. The only thing is that the programmer has to be very, 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 very careful. And when using Scala, Haskell, and this type of programming languages, what we have is the help of the compiler. The compiler won't let us down and go and make a nonsensical, non-logical things. What we have also is that the design patterns that we have in functional programming, you saw there is this bfunctor class or this semi-groupal type class in the CATS library and many other libraries. The compose function, higher order function, this corresponds to common deduction schemes in logic, and this shows that the way and the design patterns that we find in functional programming are in many ways logical. So, do programming with types help us to be better programmers? Well, in my opinion, yes. Why? Because, well, not only because of understandability. Type signatures, we saw that they tell us in many cases all that we need in order to provide implementations. Okay, but also reliability. I mean, it doesn't make sense to test to do unit testing for this composed function. It is already proven by the compiler. Okay? At the level of the methodology, this correspondence between logic and computation and being aware of this correspondence allow us to perform or take design decisions in a more logical way. Okay, and it is in my experience that we argue less when doing functional programming than when I was doing object-oriented programming some time ago. Finally, it is logic. I think that programming with types help us to be better programmers because it is a joy to program with types. So some reference, type-driven development. In Idris, you have this book, which is a very, very, very nice book. Also, if you want to learn functional programming, I recommend this functional book by Runar, Paul, and this last version with Michael Pilkis as well. This tutorial is really, really nice. This is a brief tutorial on the Howard correspondence by Sergei Vinitsky. This guy also implemented a plugin, a Scala plugin, for obtaining this implementation that we did with type-driven development by hand automatically, okay, using results from automatic theorem proving. Okay. Well, you have the code for this talk in this repository. Okay. Well, I hope that we see each other pretty soon. For instance, if you can, don't forget to say hi, and we hope that we start our meetups in the Scala group pretty soon. So thank you very much for your attention.